Hello, my name is Roberto Pasqualino. I am visiting researcher at the Global Sustainability Institute at Anglia Ruskin University in Cambridge. Today, I'm going to talk to you about the limits of growth World3 model. In this lecture, you will learn about the history of the limits of growth World3 model and why this model became so famous. The papers of Graham Turner, written from 2008 to 2013, to compare the World3 to historical data, that I personally consider as not being the way to use the World3 model. I will provide you with an overview on the model. We will speak about the dynamics of exponential growth and overshoot the ecological limits that made this piece of work so famous. And finally, I will provide a comparison analysis between World3 and historical data from 1995 to 2012 in the correct way. As many of you may know, The Limits of Growth is a famous series of books. The first book was published in 1972, financed by the Club of Rome, a non-profit activist and political organization that was concerned about the interaction between growth and planetary limits. The work consisted in developing the World3 system dynamics model, simulate a scenario to look at the complex net of interaction requested by the Club of Rome. The outcome of the work, as we will see thereafter, was to alarm policymakers and citizens worldwide that growth could collapse the world in the first half of the 21st century. The lead author of the work were Dennis Meadows with Donella Meadows, his wife, and Jürgen Randers. The Limits of Growth provides only the conclusion and an overview of the World3 model. So, 2 years after, they published the book Dynamics of Growth in a Finite World, with all technical details on the World3. The work allowed for the creation of IASA, the International Institute for Applied System Analysis, and the IASA Symposium for 1976 to make a call to other disciplines of modelers to criticize the World3. This was necessary to seek a real truth in it, and if global action were necessary for real. The result was the dismissal of the limits of growth by policymakers and economists of the time, since too long-term focused for their standards and because we were still far from reaching world limits. And in the end, they criticized it not for including the technology improvements in there. Thus, 20 years after, in correspondence of the United Nations Conference on Environment and Development, that is the Rio Earth Summit, they slightly updated the World3 with 20 years of historical data, called the model World3-91, and published the second book, Beyond the Limits, basically using the same scenario approach while including adaptive technology development in the model. 10 years after, they published the 30 years update report in a similar way of the second book and using the same scenario approach, improving the model slightly based on 10 years more of historical data. The technical aspect of the model remain in the 1974 book, and the updates of the new version can be found in the appendixes of the 1992 and the 2003 books. Few of you might also know that the Limits of Growth was based on the work of Professor De Forester, that was Dennis Meadows' PhD supervisor. Forester developed the World3 model based on the same conversation with the Club of Rome. World2 is smaller than World3, but contains the same meaning, and was published the year before in World Dynamics. Fewer people, if not none of you, could instead know about the book led by Donella Meadows in 1982, entitled Groping in the Dark. In my opinion, this should be the only real book to read to get insights into this piece of work. In Groping in the Dark, Donella Meadows summarizes all of her insights of the IASA Symposium, showing why Limits of Growth was actually dismissed. The book can be found online for free and definitely worth having a look at if people are interested in this topic. This scenario, taken from the last book and produced with the last version of the World3, is what made the Limits of Growth so famous. They call this the standard run or base run, and they refer to it initially as the most likely future for humanity. In this scenario, they assumed a limited amount of resources that could not allow for the industrial system to take up over a certain time, reaching resource limits around 2020 and collapsing all industrial sector and then food, population, and services. Pollution is there, but not high enough to create any harm to people. The result is global collapse by 2020. One of those who successfully managed to galvanize media and people worldwide on the doom of our global collapse based on the limits of growth has been Graham Turner in 2008. In 2008, he picked the initial publication as in 1972 and tried to check which of the scenarios published by the limits of growth better match the historical data. What he did was to compare the trends of the scenarios and the trending data of the last 40 years. He normalized them and put them in the same graph. The conclusion was that we are following the base run scenario of limits of growth, and thus we are at the cusp of imminent global collapse. He published the same concept in 2012, and he was criticized for this by another scientist named Castro. So he wrote a final response in 2013. This was a typical dispute when two scientists disagree among each other. What I'm going to tell you in this presentation is that Turner was wrong and that you just need to read the book not to make this mistake. And I'm going to tell you why in this presentation. Let's get straight in the practicalities of the limits of growth. The first thing that we should say is that they developed a dynamic model based on two concepts. These are growth and limits. Of course, the two concepts are in contraposition among each other. Growth is represented by population and capital, or you can call it economic growth. Limits are represented by ecological limits that are resources, land availability, and land quality, and persistent pollution, or rather pollutants that are harmful to human life or ecological systems. What Meadows says in 2012 is that what we meant in 1972 in the limits of growth, and is still true, is that there is no simply endless physical growth on a planet. The terminology of stock and flows that we're representing here will become more familiar over the course of this presentation. At the top level, the World3-03 is a computer model developed in system dynamics. It is composed of 8 sectors, all interconnected and feeding back among each other. These are population that grows and generates demand, industries that also grow and supply all material belongings to every other sector of the economy, service sectors is mainly representative of the health sector. Agriculture, including land, provides food for people. Finally, pollution is generated by industrial and agricultural activities, and resources can get depleted until the point in which they stop industrial production. In the figure, you can see the presence of circular causation arrows that represent feedback loops in the model. Feedback loops can be positive, increasing in magnitude over time and indicated with a plus sign, or negative. They tend to act by reducing a variable and are indicated with a negative sign, so a minus sign. The positive loops are only 2 and are in the population and industrial sectors. The negative loops are in every sector and mostly dependent on the ecological limits. The general dynamics of World3 is nothing more than a simulation dominated by the reinforcing loop from 1900 to 21st century. And eventually, since limits are reached, there is what we call a shift in loop dominance, creating more strength in the balancing loop that generates a collapse of the world. Looking at the first reinforcing loop on the top right, we go back to the dynamics of population in the World3. In this case, population is a stock that indicates something you can actually measure and count, since that is a physical variable. In dynamic modeling, the stock can change due to the flows, that in this case is about births and deaths. The reinforcing loop in this case indicates that birds are dependent on population, which will feed back increasing population at every time step. This means that in the initial population will generate birds in the next future, which will increase population again. This will require higher birds and will push population up again and so forth. Despite these being not important for this lecture, for those of you who like the math, you can see the dynamics in terms of equations in both the iterative and continuous time forms. On the one hand, you can see that the population at the time t+1 corresponds to the population at the previous time added with the net growth rate of population. Transforming this in continuous time, you get the integral, where g is the difference between births and death rates over time. If one assumes a constant growth rate g, then the solution of this equation is simple exponential growth. As you can see from this slide, a system dynamics model is nothing more than a system of nonlinear differential equations solved in continuous time. If we compare the mathematical formulation of population dynamics with the historical data, we find that, to date, population has been growing following an actual exponential growth rate. The figure here shows the possible forecasts from the United Nations Population Division, where they range from an average expected case, this is the dashed line, reaching about 10 billion people by the year 2100. To a high growth case, keeping exponential growth further, to a low case in which maybe a demographic transition will help people have less children than in the past. The right curve is no more than the result of our future action and thus can be assessed only in terms of uncertainty today. The second reinforcing loop is probably more interesting and more concerning as well, in particular in relation to the meaning of the limits growth. This works very similar to population growth, since a stock of capital or factories can generate more output, which will support higher investment, which push capital even further. As far as investments is higher than the obsolescence of discards or discard rate, the result is exponential growth. If you look at the average global GDP growth rate in the last 60 years on the left-hand side, we will find that this number is approximately 3.6% per year on average. On the right-hand side, we assume a constant 3.6% increased growth rate in comparison to the actual GDP in 1960. As you can see, the real curve is quite close to the exponential growth path. The concerning fact is that the 3.6% exponential growth rate per year corresponds to doubling the economy at every 20 years. If you give a closer look at the graph on the right, you will see that if you normalize the GDP at 1 in 1960, it will reach approximately 2 in 1980 and 4 in 2000. Their future should be an economy being approximately 8 times bigger in 2020 than what it was in 1960. One of the problems of exponential growth is that in order to understand it, one needs to make the calculation. So we can do this very simple iterative exercise that you can do everywhere. The idea is to pick a sheet of paper and try to answer the question how thick that is. If you consider a block of printing paper of 500 sheets, that is about 5 centimeters. So the division gives about 0.1 millimeters. If you fold it once on itself, the thickness will double up to 0.2 millimeters. If you do it again, that will be 0.4 millimeters. The big question is, without using a calculator and assuming this is impossible to do at all, could you please give an intuitive estimate on how thick you think the sheet of paper would be if you fold it another 40 times on itself? I repeat, folding these again another 40 times. At this point, I should suggest you to stop the video on your screen, just giving you the time to give a thought on this. I will instead move to the next slide to discuss the answer. As you can see, after 2 times we get to about 0.4 millimeters. The more we start holding this on itself, the faster the growth become. And just in 14 times, we can get to approximately 1.6 meters. After 20 times, we already overtake the 100 meters. After 24 times, we managed to surpass 1 kilometer. After 34 times, we get to 1.7 thousand kilometers. And after 42 times, so the number 42, we get approximately 440 kilometers. This is quite an astonishing result for most people who normally guess something like 1 meter or maybe 50 centimeters and even less than that. But it can be quite interesting to see that folding a piece of paper on itself 42 times can generate some kind of distance between the Earth and the Moon. So congratulations. If you think this thing is possible, actually we can look at the exponential growth of population dynamics over the past 10,000 years. As you can see, in the last, let's say, 100 years, we managed to grow much faster than all in the past. And that's actually exactly the dynamic of exponential growth. Now, let's start talking about the overshoot problem arising from the limits of growth. You might have heard about the Global Overshoot Day. It was on the 8th of August in 2016, 2nd of August in 2017, 1st of August in 2018, 29th of July in 2019. As you can see, it is decreasing over time. The overshoot day is normally linked to the question, how many Hertz are we using this year? In order to understand what the overshoot day is all about, it is good to start from something a little bit more tangible. Have you ever put weight on? I did. I do all the time. Despite being a not very happy example, it explains the concept very well. If you consider the mass of your body, it is as simple to realize that if you eat more calories than what you actually consume, you will increase in mass. If you eat less, you will lose weight. And if you eat the same, you should be able to stay in balance. One particular characteristic of our body is that we cannot control much the calories we burn. If one assumes a basal consumption of your body at about 2,000 kilocalories per day, then the average diet could consist in, let's say, 500 kilocalories for breakfast, then 800 kilocalories for lunch, and then maybe 600 for dinner. At the end of the day, we are at 1,900 kilocalories, and we feel a little hungry and feel for something sweet. If you decide to eat an ice cream of 300 kilocalories, let's say, at the time, the bite that let us go beyond the 2,000 kilocalories is that one of the daily overshoots of our actual consumption to our basal consumption. The solution to these overshoots, to go back to desired weight, can be various, such as eating less for a day that come after, doing sports, or going to the gym. So at the end of the day, it can be quite a simple concept to solve. The problem of the global overshoot is exactly the same, but a bit more complex. The carbon in the environment and pollution are the mass of the body. The natural absorption of biocapacity of our waste and pollutants has strict limits, similar to the basal consumption of our body. The problem is that as far as population and the economy grow, and they keep generating those emissions to the environment that are higher than the biocapacity, the ecosystems become fatter and fatter, accumulating that emissions inside. It also means that the only way to reduce environmental damage is not to stop growing, but reducing our emission below the biocapacity of the planet, such that it can start reabsorbing it over time. This is a difficult challenge given the constant need for the economy to grow. The world ecological footprint is the main measure to estimate this today, and there are various ways to come up with a number. According to Beeser 2016, the overshoot is only one around the year 1970s, where actually the limits of growth came out. And today we are approximately using 1.7 planets while still growing. And it is why the overshoot day is anticipating a little bit every single year. Going back to the limits of growth of 1972, here we show the second scenario of their concern. Since they could not be sure that the resource limits were the constraints of the world, they tried to simulate what happens in the model if you assume way more resources are available. The result was the following. From present time, we grow a little bit, increasing, most importantly, the speed of resource extraction and pollution generation. As you can see, population and capital are bigger than what they used to be in the past. As a result, that's the reason why the resource extraction gets faster, because we have a bigger economy. As you can see in this picture, the food starts there to grow a little. What happens next is that pollution will go up, become dangerous, let's say. Resources decrease, but not going to zero. The food system gets completely impacted by the pollution sector, just getting destroyed. And the result of it is that population will start decreasing because people starve, and as a result, also industrial output will collapse. This scenario became the base to run all the other scenarios that were assuming that some technology could solve every limit problem and allow the system to grow further. All technologies were considered as increasing cost and reducing growth a little. The final goal, differently from what Turner was saying, was to find a way to avoid the overshoot of growth to global limits. This was the purpose of the limits of growth. In the slide, I repropose the scenario 2 from the latest publication of limits of growth in 2003 using the World3-03 model. As you can see, the adjustments of the model generate a slightly different behavior, but maintaining the same conclusions. This was followed by the scenario 3, where the applied pollution technology realized that the world could collapse because of the food system was not capable of producing enough. They managed to apply food yields improvement technology, finding that the world could collapse because of land erosion. They managed to apply technology that could support lower land erosion, but the world collapsed because we have too much resource consumption again. Then they make a technology which improves resource conservation, assuming, for example, green energy or things like that. But this, in the world model, doesn't do much than postponing collapse due to the high cost of all the technologies put together. Here I show the scenario 6 directly. That was the one where they assumed that all the technologies were adapting to the solution of the world environmental limits. This is hard to say, but somehow this scenario is also the only single opinion that the Dennis Meadows and Jorgen Randers had in 2003 about the most likely future for humankind. This includes a quite harmful pollution for the food system, generating a food crisis from 2020 to 2070. In general, they are assuming a general decline in material well-being for people, mainly due to the high cost of technologies applied to solve the environmental problem. This is my and my team contribution to the limits of growth literature from 2015. Based on the analysis of Graham Turner, we decided to try to put in the model historical data from 1995 to 2012 from the public resources such as World Bank and the FAO. This is what is called a calibration in modeling terms. The results have been very interesting and positive in general. The chart showed the historical data in dots, the scenario 2 of limits of growth in dashed lines, and the calibration as a continuous line going through all the historical data. As you can see, there is quite a difference from their expectations and the actual real data today. First of all, industrial output at the top left results being lower than their expectations. Secondly, services at the top right grew much faster and are expanding faster than what they were expecting. This means that there was a shift in economic paradigm towards a service economy rather than a material one, which also is less linked to pollution emission than what the World3 was actually expecting. Then you can find that arable land is following a different path than the simulation, being mostly stable today. Population birth rates were well catched. Last, you find life expectancy being lower than expected, which also means that we, as population, have lower impacts on the environment than what they were expecting. The study confirms we are still growing and doing it exponentially, but if we simulate this further, we will find that reaching the global limits can happen sometimes in 2050. This is not too bad overall. As summary, World3 and the various version of the model is a system dynamics model linked to the publication of very famous books. One of the main findings was to show the concern for exponential growth in a finite planet, which is not a possible phenomena overall and still holds true today. The possibility of overshoot is still real, in particular given the ecological footprint indicator and the state of climate change today. Their thesis of not sufficiency of using technology to solve environmental problems still also hold true today, since removing one limit will simply postpone time for the actual overshoot unless we stop growth. Turner, despite contributing positively to the debate, did not make a good use of the World3. We can say that. A possible opinion of the model originators on the state of global ecosystem to the end of the century is rather a food crisis and lowering the living standards for most people globally. As a criticism, we can also say they did not model explicitly important elements of the limits, such as climate change and green energy. These were partially considered in the pollution and resources dimension, but not the same thing really. Finally, World3 could be used to demonstrate we are on better track than the collapsing scenarios of the limits of growth itself, showing the shift to the service economy as engine for growth. Hoping this presentation was interesting and clear for you, I leave you with the references of the talk. Thank you for listening.